Now here's some data that we obtained in class. In a time interval of 1.2 seconds, the beam rotated from its original position out to a position, let's say here. That was under the influence of a washer falling over the pulley. And then from here to here, we coasted to a stop in 3.02 seconds. And we want to know what the angular velocities, angular accelerations, and so forth might have been. By drawing right triangles, we find that the first ray forms a triangle that has an altitude of 3.2 and a base of 8, or an opposite side of 3.2 and adjacent side of 8, or y equals 3.2 and x equals 8. Using what we know about finding the angle from the sides, we take the inverse tangent of the y-coordinate over the x, and we get approximately 0.38 radians for the first angle. Doing the same thing here, we did a right triangle here. I didn't label the sides, but I did indicate where the triangle was. We took the inverse tangent of the rise of the y-coordinate over the x-coordinate, and we got theta 2 is 1.13 radians. And then we proceed to analyze the motion. So during the first phase of motion, we start from theta equals 0, end up at 0.38 radians. The 0.38 radians between the start and the point where the washer hits the floor of the table or whatever, and a delta t of 1.2 seconds as we measure with the computer timer. And we get delta theta, a change in angle of 0.38 radians, from 0 to 0.38 radians in a time of 1.26 seconds, and this tells us that our average velocity is 0.38 radians over 1.26 seconds, 0.30 radians per second. This is not just a velocity, it's an angular velocity, so instead of v we call it omega. And since it's average, we put the bar over the top. So we have omega bar is 0.30 radians per second. If the acceleration is uniform, which is what we're assuming here, and we'll look at and see if that assumption gives us consistent results. We go from omega naught equals 0 to omega f equals 0.60 radians per second, change in omega of 0.60 radians per second, minus 0 radians per second, of course, because that was our initial velocity, or 0.60 radians per second. And this gives us an average acceleration, change in velocity over time interval. Okay, our change in velocity is 0.60 radians per second. Of course, that's an angular velocity, so we use omega. Divide by time, which is 1.26 seconds, time interval, and we get 0.48 radians per second squared. In the second phase of the motion, our initial velocity is 0.60 radians per second, if we believe what we got in the first phase, because the second phase begins where the first phase ends, and this was the final velocity in the first phase. Final angular velocity is 0. Time interval was 3.02 seconds. From this we calculate omega bar, average angular velocity. And actually I think we might have an error here, so I'm going to stop right now and then we'll pick this up in the next clip.